Hey guys, welcome back to another episode of this shit. Um, we're doing another worked example problem for topic 5. We're covering enthalpy changes of formation. Um, we're going to do question 25, and we're also going to do question 26. Um, Pause the video now if you want to try both of them. Alright, I assume you've come back, so let's switch over to the whiteboard, or what I call them as paint. Now, when you're given formation enthalpies, it's pretty simple what the it makes your life is pretty much made quite simple. You don't have to do any of that Hess's law bullshit. You can just do product minus reactant. Or more technically, it would be the sum of the moles of products times their delta H of formation, subtract the sum of all reactants times their delta H of formation, which that's the more formal way to put it. Now, um, this is probably not very helpful to you, so I'm going to try and show you why this formula works the way it does. And I'm going to try and prove to you that this actually does work. So, um, well, I'm going to show you another way that it works, but here, let's just go to the first question here, and I'll show you it to using Hess's law that you do in fact get the same answer, and you don't necessarily have to do the whole process. Sure, it takes more time to do it the Hess's law way, but if you just wanted to do it one way, I'm going to show you that you could indeed just, do it that one way. So let's write it up top. So Fe3O4 plus 2C yields Fe, 3 of them, plus 2CO2. And if we did it the products minus reactant way, we know that, remember that there's zero enthalpy change of formation for standard state elements, so it would be 2 negative 393.4 plus 3 times 0, subtract 1 negative 1118 plus 2 0. And we get 330 kilojoules as the answer to that. When we do the math, we get 330 kilojoules, about plus 330 kilojoules. But obviously, that's nice and good. We have an answer, but let me show you that this works. So let's use our good old friend, the Hess cycle. So I'm going to note what delta H was, and then I'm going to erase this all. Now, we know that Hess's law states that it doesn't matter how you transform between this set of chemicals and this set of chemicals, the difference in potential energy is always the same, or delta H is always the same, no matter how you transform that set. So, Hess's law was, I think, a good example of showing you reactions in terms of steps. So, so using that fact that delta H is just, you can transform from one set of chemicals to the other set of chemicals by a series of steps. Let's show that. Now, the definition of enthalpy change of formation is forming 1 mole of compound from its constituent elements. So we can sort of, from its standard state elements into that element under standard conditions. So we know that that's the enthalpy change of formation. So using that, we can write out a reaction to denote that. So to form 1 mole of Fe3O4. And similarly, so that would be a 3 and that would be a 2. So that would be equation number 1. Equation number 2 would be C plus O2 yields CO2, and this is fixed at 1 mole of compound from its constituent elements, and it happens to be that these happen to be balanced. And so let's add them up in such a way so that we can get our delta H. Now it looks like this first one has to be flipped, so I'm going to attach a minus sign there and flip it, flip the reaction around. So let's flip that. I kind of messed up that arrowhead, but that's fine. And then it looks like I have to double the second one, so I'm going to denote that with a double there to denote what I have to do to delta H, since we should be familiar with using Hess's law manipulations by now. And then so 2, 2, 2, and then remember, if I add up the reactions, I remember I have to add their delta H's, which I'll now do. So 1, 8, 2 times negative 393.8, which if I add them up, so I get Fe3O4 yields 3Fe plus 2CO2. And I can make sure that everything works. 2C plus, I forgot the carbons there. Those two can cancel out because they appear on both sides, and we get the reaction above, and we get the delta H. Delta H equals, and we get that delta H equals the exact same thing, 330 kilojoules. Right? Pretty simple. So that's sort of, I guess, I don't know if you would call it proof, but that's showing you that it works the same way. And in reality, the idea here behind Hess's law is that you transform the set of chemicals, the reactant set of, you transform the standard state elements into the reactants. You also transform some of them into their products, and you can measure the enthalpy change by going from, another way you could visualize it is, okay, you break every single thing and remake it into atoms. So that's that's just the negative enthalpy change of formation, and then you take all those elements and turn them into the products. So that's what the enthalpy change of formation is. You really are just going reactants to their standard state elements, and then from their standard state elements to their products. And you know that the net enthalpy change is from reactants to products. So in order to calculate that, we would work our way backwards. So we could do reactant minus product. And that, hopefully, me showing it this way sort of gives you a clue as to what we're doing. So here we're quite literally, so here, where's my pointer? Oh, here it is. So here we are literally breaking the bonds. We are decomposing this mole of reactant to its standard state elements, and then we're reacting this standard state element into its product. And from that we get the net enthalpy change, right? So hopefully that makes sense. Now, to really rub it in home, let's do the next question here, 26. So hopefully now that sort of why you understand why that we do it the way we do, let's see if you could do 26 on your own. So 26 here, 2NO2 into N2O4. Let me go back to the question here. Pause the video if you want to try, and come back for the solution. Alright, so presuming that you're back, we can again do product minus reactant because we're given formation enthalpies. So P minus R, which is 9.2 subtract 2 times 33.2, which yields in a enthalpy change of 9.2 subtract 2 times 33.2 minus 57.2. And that's all there is to it, really. There's really not much to this topic, and I personally can't find the difficulty in it, despite people having great difficulty. Conceptually, it's quite difficult, but I think the problems are more straightforward than people think. But people seem to disagree with me on that one, and I can see where the difficulty comes from, especially um, trying to approach it conceptually. But really, the formula. Hopefully, I showed you why it makes sense and why it works according to Hess's law, because we're just going from product breaking all the bonds to form their standard state elements and then reforming them into their products. And hopefully, by doing it that way, it sort of sheds light on how really intuitive this is. So, thank you for watching. Don't forget to like and subscribe, all that fun stuff.